In the previous part, we saw the basics of what statistical learning is, as well as the perceptron algorithm. Let's talk a little bit more about the perceptron algorithm, and in particular, trying to understand more about how this algorithm works, and what we can say, and when it works well, maybe when it doesn't work as well, and stuff like that. Okay, so first of all, what we're going to do is talk about the goal that we were looking at before. So before our goal when we were learning was really to come up with something that had the following properties. I'll just kind of claim this, but we'll see how it's kind of equivalent to before. So we're trying to go for something which is like the following, that we have this type of relationship. We're trying to learn so remember, x and y's are the data set we're given in, and the w's and the b's are the parameters that we're trying to learn. And the idea is we're trying to learn these w and b such that we have this guarantee for all I in our data set. So that's the guarantee that we're going for. But let's simplify this a little bit, or try to write this a little bit differently. So there's one trick that's very common to do, which is known as padding. So it's kind of ugly to have just the inner product of these two things and then you add something else on. Well, this can equivalently be written as the following. We can also write this as the inner product of w, and we have a 1 here, and we take the inner product, w and b here, and we just pad on to this input vector xi and a 1. So that's a simple trick that people do. And another common trick is to kind of pre-multiply these things by just sort of a different way of writing it. But another thing you can do is, this is kind of equivalent to saying that yi times w b inner product with xi 1 is going to be greater than 0. That's kind of what an equivalent way of saying that this is an equivalent way of writing the sign thing here. Therefore, a convenient thing that we often do is, what's often done is we convert our training points. So instead of, if we're given a point xi yi, just something like this, we're given some point in our training set like this, what we'll do is a transformation to write it as follows, as yi times xi 1, and then we just write this as let me do this. We call this new thing AI. And the reason why this is kind of convenient is because a very easy thing to, an easier way to write this sort of training goal that we're trying to do, we're trying to have that it has the correct prediction on all the training points, is to do the following. We can just write it as follows. So we can just write, we want that the, what do we want? I guess the one way of writing it is like the following. You just say that AI inner product with W is greater than 0 for all I. And this time this W is kind of augmented in the sense that it's going to contain this B as well. It's kind of like, it includes the bias in it as well. So that's one way to write our training goal, which is kind of just a massaging of what the intuitive thing is. We want everything to rely on the correct side of this straight line. Well, another way to write this is just as follows. You write A times W is greater than 0, where this is like a vector. And this means like an entry-wise guarantee. Cool. So that's kind of an equivalent way of writing our goal. So just kind of think, hopefully the former one here makes sense to you, where you're trying to get the correct sign for each point in your training data. But if you massage it enough, then you'll get into something which is kind of like this. You have a set of vectors which you stack on top of each other. Oh yeah, let me be clear about this. So how do we form this matrix A? Well, we just basically stack these vectors on top of each other in matrix form. So this is in kind of Rn by d plus 1, because there's n rows and d plus 1 columns, one for each of the feature vector dimensions of the feature vector plus the 1 at the end. And you essentially want this A matrix times this parameter vector to be greater than 0 entry-wise. Good. So hopefully this makes sense. This one is just a massaging which follows naturally if you just follow the mathematical derivation here. Cool. And this padding is very common in machine learning, so don't be too scared if you see like sometimes this B is missing, sometimes it's there. It's often just swallowed up into the parameter vector. Good. Okay, so this is what our kind of goal is. That said, we can't always solve this problem in general. Why is that? There might be it might be impossible. There might not exist any such W which does it, depending on the data. Like to give you an example as to when this might not be possible. Well, let's just give you a pictorial representation, and you can sort of fill in the blanks and see what this means in terms of matrix A. But you can imagine, for example, if you had some pluses over here, and then you had some minuses here. Well, and then what if you had a minus over here, kind of on the other side? So in this case, it turns out that there is no way to draw a linear separator which will separate the plus points and the minus points. And therefore, there's no way to ever basically come up with some sort of W which will be able to, W and B, which will be able to separate the data as we want. Therefore, this might be impossible sometimes in cases like this, but when it's not, we call the data linearly separable. Let me erase this. But okay, let's talk about what linear separability means mathematically. So linear separability is the following guarantee. We say that a data set is linearly separable if we're going to use it for basically the rest of this lecture, we're going to use this type of representation, this A's, which does the padding and pre-multiplication. But we say that a data set is linearly separable if there exists a W. So linear separable means there exists W such that AI inner product with W is greater than or equal to S for some S greater than 0 for all I. So yeah, the idea is it's going to be linearly separable if you can take some sort of some sort of parameter vector, take the inner product with each of the points, and say that it's greater than some S which is non-zero. And yeah, a way to write this is we can say instead, if you prefer the matrix notation, we say that A, kind of equivalently, that A times W is greater than or equal to S times the 1 vector, where S is greater than 0, so S is some constant. So if this is not the case, then we say that S is not linearly separable or linearly inseparable. And sorry, let me just make it clear that S has to be greater than 0. Now let me kind of try to show you what this means pictorially, this linear separability. So maybe I shouldn't have erased this. Let's draw it again. But imagine we have some points here, and then we have minus points over here. And strict linear separability means that you're going to essentially have some sort of, this is a technical term and we'll talk about it a bit later, but you have to have some sort of margin that these things lie, they're separated from the actual hyperplane here. They're not going to be anything lying exactly on the this separating hyperplane, but there's going to be some distance between it and any point that you look at. So that's kind of what linear separability means. Hopefully that's clear. Cool. So now we've got this great algorithm, the Perceptron algorithm, and what it'll do is it'll just run for a bunch, and the hope is after running for a bunch, it'll eventually terminate, and everything will be classified correctly. So will it though? Like, we don't really have any guarantees. I just ran it for you a bit and I showed you that it kind of works, but does it actually work? Do we have any guarantees that'll converge, or maybe that'll ever end at all? And yeah, in fact, there's what's known as an error bound on it, which I'll say for you. So what we're going to say is the following. Suppose that, so remember, all we're given is we're given some A. So suppose that there exists some W and S greater than 0, such that we have that AW is greater than or equal to S times 1. Then we have that Perceptron will converge in a number of steps that I'll write as R squared times, let me write this, I'll write this and explain it. L2 norm squared divided by S squared, where R is equal to max over I of the L2 norm of AI. Okay, and if you're not familiar with this norm notation, then you should get familiar with it because it's very important. Yeah, basically the L2 norm of a vector says that you square all the entries, add them together, and take the square root. So here's the theorem that we have here. Suppose that if there's a solution to it and it's linearly separable, then Perceptron will converge in less than or equal to this many steps. And let's parse each of these different things. So first of all, let's take a look at this. We can see that the number of steps that it's going to take scales quadratically with the max of the L2 norms of the points. So essentially what this says is that the bigger the points, then the more steps that the algorithm will take. So let's try kind of give you an example visually as to why that is, or what's really going on. So the idea is kind of the following. Compare, say, something like this, where you have, say, maybe points which are kind of close to the origin, if they're all around here, and then you have some minus points over here. Then the idea is that you don't really, it's going to take only small steps whenever the Perceptron algorithm is running, so you're going to not really go very far. And this problem is, in some sense, much easier than a problem which looks something more like this. Say if you have points way over here and way over here and over here, and then meanwhile you have points over here and over here, let's say. So the idea is maybe this one's a lot harder. Here's some intuition as to why. So this one, let's just say that this instance would take more time to converge than this one, according to this theorem. And you can kind of see the reason why intuitively, because remember how the algorithm works. Whenever you see a parameter, whenever you make a mistake, you update the parameter by whatever point you're looking at. So you'll note that when it sees a point like this one or this one, this is a much bigger point, and therefore you're going to take a big step in terms of the vector. So you're going to have the parameter vector W maybe jumping over here, and then you see something over here, and then it'll have to jump over here maybe, and then it'll make big steps for a while. But it has to, you can see that the linear separator has to fall somewhere in between these two things right here. And so if it's taking big steps like this, there's not really any guarantee that it'll take a while longer to find out where exactly this thing in the middle is. That's just one kind of intuition saying that the further away the points are from each other, the then the longer the algorithm will take to converge. Okay, so that's just one part of the number of steps. Now, what about the other part in the number of steps? Well, this is a little bit of an oddball here, in the sense that you might be wondering why, what's going on here. Basically, it says that the bigger the W parameter is, and the smaller the SR, then the more steps it'll take. Now, this is kind of weird, right? Because, well, how do these come into it at all? But the thing is, let me show you how we can kind of optimize over this type of bound. So what do I mean by optimize over this type of bound? Remember, let's see what the theorem says. It says that if there's an if there's a W and an S that is like this, then perceptron will converge. However, there's not just one W and S that satisfies this. For example, I could always multiply both sides by 2, right? So for example, here's another thing that if we have this solution, then another solution is something like 2W is greater than or equal to 2S times 1. So you can see that if there's one solution, that there's another solution, and there's in fact many solutions. There's infinitely many solutions. We could shrink these down, we could shrink them up, so on. In fact, they don't even just have to be linear scalings of each other. For example, let's take a look at, there's sometimes many different solutions. So if we had, I'll draw a picture yet again, we had something like this, and then we had something like this, then in fact there's many solutions that will separate them, right? In the sense that we could put one line over here, that will be a linear separator. And if you sort of do the math and write this mathematically, it'll correspond to some W and S. There's also one over here, which would correspond to a different W and S. And there's one over here also, which would correspond to another W and S. So there's many different types of solutions to this. There may be, depending on the data set A, many different parameter vectors W and S, which would lead to this inequality being satisfied. And correspondingly, each of them would lead to a different term here, which gives you the norm of the W divided by the S squared. So what we'd like to do is, for the sake of analysis, we would like to picture that we have the W and S pair, which minimizes this quantity, because this is all just for the sake of analysis. So if we pick the one which is smallest, that will result in the fastest and the tightest convergence bound for the algorithm. So good, let's try to take a bit more of a look at that, and we'll see how the interpretation of that goes. Cool. So what's really going on here is, let's look at that term. Essentially, we're trying to do is we're trying to essentially minimize this. So we want to minimize this term here, which kind of determines how many steps we take, and we want to minimize it over everything which satisfies that. So minimize over all W and S, such that AW is greater than or equal to S times the 1 vector. Good, so that's what we're trying to do, and we want to pick the ones which minimize this. And the first thing we can do is, well, we can kind of just deal with a, say, constant. We can always rescale our data. So let's just look at a fixed scaling of our data, in the sense that let's pretend that this W is going to be equal to, the unit norm of the norm of this vector W will be equal to 1. So this is kind of related to this thing which I said before, where we could always have 2W and like 2S. Well, the idea is, what if we just pretend that we put a constant in front of both W and S, such that W is a unit vector? So we can do that, and we can always scale S correspondingly. So a kind of equivalent optimization problem will be to look over this for all unit vectors W, as well as the same constraint as we had before. The minimization over all this, and now we just have 1 over S squared. Now, the next thing we're going to do is note that since this is a minimization, well, if we put it in the denominator, then it's going to be a maximization. Because if we're minimizing the whole thing, that corresponds to maximizing the denominator. So this can be written as the following. And we can also pull it inside the squared. So let me just write it, and hopefully it'll make sense to you why this holds. So we can write it as the following: maximum over w comma s with w2 equals 1, a w greater than or equal to s times 1. And we have s here and the whole quantity squared. Cool. This is getting a bit weird. Why are we doing all this? But we're almost done. And the final thing I want to say is that this can be written as the following. So I'll write it and then we'll see why. So max over all unit vectors w. And we take the min over all I of ai w. So this is perhaps the least obvious step as to why we're doing this, but let's take a look at this constraint here. We're taking the we have the constraint that the inner product of a times w is going to be greater than or equal to s times the 1 vector. So this means an entry-wise bound where we want essentially each row of the product a times w to be greater than or equal to s. Well, think about, and then we're maximizing s over that. So the idea is that if you look at each row, you take the value of that product and you take whichever one is going to be the minimum one. That corresponds to how large you can set this s to be. Because if it was loose, then you could have increased s to match up to it. So essentially, you might need to think about this a bit, but please try to figure it out, and you'll see that you can actually you can rewrite this as the following. So now we have this kind of odd expression here. This looks even more confusing than what we started, but I claim that this is nice and a convenient problem to solve in the following sense. So this quantity here, this is what's going to be known as the margin gamma, which we call gamma. So what is this term here? It says essentially you pretend that we're looking at a unit vector w, but what you do is you take the min inner product of ai and w, which essentially tells you how far the data is from our separating hyperplane w. So this is a bit of a mouthful, but let's try to see an example, and hopefully I'll give you an intuition as to what exactly I'm referring to here. And maybe it'll match your intuition as to which problems are hard versus easy. So here's two different, I'll give you two different instances. Suppose we had some instance which looks something like this, where we have maybe points over here. And we had some points over here. And you might be thinking, okay, this is a very easy problem to solve because, like, I don't know, the points are very far from each other, and I can very easily see that there's a million lines which separate them. So that's because this is what's known as a data set with a very high margin. And on the other hand, imagine we have a data set which looks something like, let me just draw another one below. Imagine you have a data set which looks more like this, where you put, say, a bunch of points over here, and you put a bunch of points over here. You might be thinking that, okay, this is a lot harder to solve, if it's even solvable, due to my poor drawing skills. But yeah, you can see that there's not really too much space to draw a line between these two. So you can see that this, intuitively at least, you might picture that this is a much harder data set to solve in terms of finding a linear separator than this one, which is much better separated. So this is what's known as, this is kind of what this expression here is trying to capture. in the sense that you'd expect that the Perceptron algorithm can learn this data set and can find a separating hyperplane a lot faster than it can for this one, because it's very hard to separate here. And this says that, yes, that's true. That's how the Perceptron algorithm works. Now, it's based on the parameter or the quantity known as the margin. So what is the margin? The margin says the following. Consider all the possible half planes that you could have to separate this. So for example, you could put something here. That's one half space that separates them. And here's another half space that separates them, and so on. But the maximum margin half space, or maximum margin linear separator, is going to be something like this. And intuitively, you can kind of see that, okay, it's kind of in the middle. But the idea is it should maximize the margin, where the margin is the minimum distance from the line to either one of these points. So I guess it should be something like this. Yeah, so I guess the margin is probably this quantity here, like how the magnitude right here to here. So you can see that the margin is fairly large here, whereas here the margin is very tiny. I can barely even draw the line between the two without them touching. So if the best separating hyperplane is very close to points on both sides, the maximum margin separating hyperplane is close to points on both sides, and it'll be harder for Perceptron to learn. And if it's very far, then it'll be easier to learn. So that's the concept of margin. And this is a very important concept in machine learning, which essentially tries to give you some idea of how easy or hard a learning problem is, which is kind of, I think in my mind, a little bit intuitive once you get used to it. Okay, I also want to comment on uniqueness, and maybe based on the discussion we've had so far. Yeah, uniqueness. Is there going to be a unique solution to Perceptron or not? And you can see that in linearly separable data sets, that in fact it's not, there's not generally going to be a unique linear separator. For example, in this data set, I can draw many different lines which work, and Perceptron, it doesn't really have many guarantees in terms of which one it finds. It's just going to find, so yeah, what does this theorem say? This bound says it converges to a separating hyperplane, which I didn't write here, but that's what it does. It essentially says that it's going to converge to some linear separating hyperplane, but it doesn't tell you which one. So it could be a good one, it could be a bad one. There's no real guarantees. For example, it could converge to this one, which is not the best one. The ideal one is kind of something around here, at least in terms of maximizing the margin. So all I want to say is that the Perceptron solution is not unique. There are other approaches which are unique and actually find the best solution in the sense of the maximum margin. And those are things called support vector machines, which we're going to return to in a few lectures. Cool. What else do we want to say? Yeah, so an important point that we have to say about this is that what happens if the data is non-separable? So for example, all these data sets which I've drawn here are separable, which is very nice because that means the Perceptron convergence theorem that I put here, that says that it's actually going to halt. But if it doesn't, then you're kind of out of luck. Say you have a minus over here, then it'll, okay, sorry, that's still linearly separable. Let's suppose you had a minus over here, then it would actually never halt. And in fact, there's theorems that say that the Perceptron algorithm would cycle. It's going to kind of start repeating parameters again and again. But yeah, if you have a non-separable data set, we can say that Perceptron cycles. And in general, Perceptron is not the right algorithm to use here. What do I mean? It's just not the right algorithm because yeah, this is a very important thing to take note of. Whenever you're using a machine learning algorithm, there's some assumptions you make about your data and what our data generating process is. Perceptron in particular assumes that our data is going to be linearly separable. So if it's not linearly separable, Perceptron is never the right algorithm for that case. At least, yeah, I can't say it is. So there's other algorithms we will see which are better suited for that type of case. So always be sure to know what sort of assumptions you're making implicitly when you choose a machine learning model. Okay, then there's some questions on when to stop. So you run this for a while. When do you give up? Well, there's many different ways, times when you know how to stop. First of all, like when maybe all points are classified correctly. That's one way, of course, is kind of implicitly what we've been talking about. One is when all points are correct. Another time is when error stops decreasing, which is essentially basically the same thing, I guess. For example, if all points are correct, then it'll stop decreasing. This could be either on the training data set or a validation data set. And then another thing is when the weights converge, meaning that essentially you do some updates and it doesn't really change much. So these are all valid ways to times to stop. And also maybe you maybe have a fixed number of iterations. Say we're going to run it for 100 times, and then whenever that's done, then we stop. So these are all reasonable ways to choose when to stop for Perceptron. Okay, and as the final thing we'll talk about today is multi-class. So multi-class meaning, so far we've just talked about things being 0 or 1, yes or no. Well, of course, there's also settings where we'd want to maybe say, is it 0 or 1 or 2 or 3? Like there's many different labels. Say, is it a cat or is it a dog? Is it an owl? Is it an eagle? Is it a mouse? Or so on. So there's some cases where we'd have not just two different labels, yes or no, but many different labels. And there's a few different ways you can generalize Perceptron to these two different cases, to this multi-class setting rather. One way to do it is what's known as one versus all. In this case, what we do is essentially, we train K classifiers, where K is the number of classes. So number of classes, where, say, with binary, then K equals 2. So far in this class, we've looked at K equals 2. This is binary. So yeah, just train K classifiers. And the idea is that what we do is we train K classifiers where each one will set one class, the corresponding class to be 1 and everything else to be -1. So for, let me write this a bit more carefully. For ith classifier, what's the way to say this? We'll say that we change the training data set such that item, like, I'll just say this in words rather than trying to write it down. Essentially what we're going to do is, for the ith classifier, we're going to look over all our data sets and all our training data, and for each point, if it has the label I, then we're going to keep it as is. If it has any other label that is, or sorry, if any point in our data set has the label I, then we're going to set it to 1. And if it has the label besides I, then we set it to -1. So the idea is we're going to kind of reduce this to the problem where the label indicates, is the label of this point I or is it not I? And so then for this specific classifier, you can train it to try to predict whether it's I or not I. And then you'd have K different classifiers, which can each essentially predict whether the label is going to be each of the possibilities. And so all that you have to do is train these K different classifiers and then run them all on your data and see which predictions come up and choose the majority, whether which one it's going to be. Okay, rather it's not going to be the majority, but it's basically going to be the value of how far it lands on the side. For example, if you pick, you're going to basically come up with some parameter vector wi for the ith classifier, and you take the inner product with the parameter x times b, and you're essentially going to choose the one which makes this as positive as possible, so that, yeah, that's kind of whichever one lies furthest on its side of the hyperplane. So pick largest I. That's one way that you can make it multi-class. Another way to make it multi-class, which I'll tell even fewer details about, is the 1 versus 1 setting, where instead of training k classifiers, instead what you do is you train k squared classifiers. So k squared classifiers. And the idea is you're going to, for each pair of different classes, or roughly k squared classifiers, but for each k and for each possible label I and j, for each pair of possible labels I and j, what you're going to do is you're going to ignore all other points which do not have one of those two labels, and then you're going to just train a perceptron on those sets of points, and that'll give you a prediction whether it's going to be from one thing or the other. And the idea is you just train several of these classifiers, and anything, any new point that you get, then you run all of these k squared classifiers on it, and this time you pick the majority vote in terms of which one is thought to win the most different comparisons between two different labels. So again, that's a bit vague. I've been vague on both of the multi-class things, but you can see more details written down in the readings. So great, that's everything that I want to say about Perceptron. It's a very classic algorithm, and it works very well when you have a linearly separable data set and you want to just figure out something. As you might be criticizing, this is not really a very realistic assumption to have a linearly separable data set, especially in modern settings, but it's something, and it's a good place to start for the first lecture.